All right, so welcome everyone and a very good morning to all of you. Thanks for attending this seminar. So it's a pleasure to host Dr. Ajit Desai from Bank of Canada. He's currently the principal data scientist from Bank of Canada, and so he holds a PhD from Carleton University in computational sciences and engineering, and he holds an MS from IIT Madras in aerospace engineering. And he is currently working on a few topics that are of great interest to the center, and that's what sort of prompted a very quick conversation, and immediately we wanted to host him here. It's a fascinating topic where they are exploring, vast, reservoir of data and trying to make large-scale inferences which are useful for economic and financial policy making. Now, that part is something which is kind of standard, and anytime people talk about application of machine learning to this kind of economic data, it's the same generic description. But what caught my eyes is that they are really utilizing some of these toolkits which are literally at the frontier, especially in terms of one of his papers that I saw. It's still a working paper, and we have been discussing. It's a proof of concept now, in the proof of concept stage, where they are trying to employ quantum computing to solve large-scale combinatorial optimization problems to make real-time decision making. And this has been so far a bit of a challenge, and I'm happy that Professor Moss and Mohageg is also there. We have been discussing this for some time, that there is, as of now, only one working paper that at least I am aware of. It came from some UPenn folks and his collaborators, Jesus Fernandez Villaverde. So what they have done is they are trying to show this new age quantum computation, and if you can actually translate it into solving something like value function iteration, that is tremendously important in solving macro models, industrial organization models, and so on. The problem is that most of these quantum computation algorithms are combinatorial optimization problems that you can solve. Whereas the value function iteration problems, or generally speaking, most of the fixed point theorems that you use, that is not amenable to this kind of combinatorial optimization. That's more like a fixed point theorem in a topological space. So there is a lot of work going on to figure out whether you can actually map it. Because if someone can actually come up with a clean theorem about how to convert this combinatorial optimization into something applicable in a differentiable functional domain, then a whole host of macro problems, so something that Mawson does, which takes maybe a week in our regular HPC to run, it will be done maybe in 20 minutes or 30 minutes. So there can be tremendous gain in terms of computation and finding out global solution in hyperdimensional setup. So that's more like a very applied math oriented motivation that I personally had. But here, one of the big reasons for inviting him was that they are also working on a lot of payments data where other types of statistical inferences are very useful in terms of fraud detection, efficient allocation of resources, etc., etc. So all in all, I think there would be a lot of learning for all of us, given the center's focus. We thank the center for allowing us to host this as a speaker. I would like to thank Ajit for accepting our invitation. It's a great pleasure to host you, and we really look forward to learn from you. You will have around 45 minutes, and then there will be a 15 minutes Q&A. So feel free to take up the questions exactly the way you see fit. I am sure there will be questions in between. So if you want to take them on the fly, more than welcome to do that. The floor is yours. Thank you.
Thank you, Professor Chakravarti. It's a really pleasure to be here. I never been at any IIM, so this is my first time, and I'm really happy to be here. And thanks for the kind introduction. So I'm a principal data scientist at the Bank of Canada, and this is the central bank or the Reserve Bank. So one of the disclaimer we have to do is these are my opinions and not necessarily attributed to the Bank of Canada. I guess Professor Chakravarti gave a really good introduction about the kind of work I've been doing. So here I will try to focus on some of the projects. A couple of them are published, a couple of them are in the working paper stage. But the whole focus is on how to make use of the payments data and the advanced analytics to improve the efficiency aspect of the payment system or to make them more safer. So either safety or efficiency, these are the two aspects we are trying to focus on. So in general, payments is a building block and economy, or you can just call it a transaction, which are mostly done in terms of the payments. So traditionally, we have been using these payments in terms of the cash. Before that, it was a barter system, so you exchange something for other thing. But now we use cash. We started using cash, and then now we are moving on to the digitalization of the world, and we make use of this Google Pay, Apple Pay, or your credit card or debit card. So more in an electronic form. So the people used to think that payment system, which settles this kind of transaction, are a plumbing system of an economy. That means like you care about them only when certain things are not working as intended. But as I said, like that with the increasing digitalization of the economy, the rise of instant payment system, which I'm sure must be familiar with, or you must be using that, UPI, or the cryptocurrencies or the central bank digital currency. So these kind of things make us rethink, should we think about this payments system as a plumbing system, or they are more of an circulatory system of an economy? And can they help us to gauge the state or the health of the economy in real time? So to back that claim, I have an interesting example. Probably I don't want to remind you about the cricket, given what happened recently, but this is a very interesting example. When I guess it's the last T20 World Cup when India was playing against Pakistan, and the last 20-25 minutes when we are chasing, India was chasing the score. In that 20 minutes, the UPI, which is India's instant payment system, the total volume was declined by about 20% compared to its normal flow. So that tells us that there is a connection between what is happening, something significant, economically significant event happening, and there is a connection with the payment system. And maybe you qualitatively or quantitatively can gauge how much that can be influencing. And that can be transferred to various other significant economic events. And this is one of the things that transferred, or that evolved from most of the developing countries. For example, in India, we have UPI. In Brazil, they have PIX. There is something in China as well. So all these countries came up with this instant payment system, which is QR code based. And now that is being adopted, or similar type of payments infrastructure is being adopted in US and Canada. So they recently launched something called FedNow, which is US's instant payment system, not necessarily very similar to UPI, but certain aspects are similar. And we are in Canada working with the RTR, it's a real-time rail, which is going to be around a similar set of similar transactions. So these are the general motivation of the research I have been looking at last 5 years at the Bank of Canada. So that I have categorized into 3 aspects. So the first aspect, I guess I motivated well, that what happens in the economy has a strong correlation with the payments. And can we use the payments data to monitor and predict the state of the economy in real time? And especially during the crisis, such as the COVID-19 period, where we had access to the payments data, which was in real time, but we did not have access to the GDP or the unemployment or the inflation, because that is being delayed with a 2 months or 1 month lag. But all the policymakers were desperate to learn that how much this COVID-19 is influencing the economy in a current state. And that's where the use of payments data was useful, because it can give us some indication that how well the economy is doing in that state. So we wrote a couple of papers. Both are now published. Then the second aspect is this payment system. They settle transactions between this large financial institution across the country. So they are a backbone or the core infrastructure of the economy, and we want to make them as safe as possible. So can we develop something which can monitor this system in real time for anything that is happening unusual or anomalous? It could be a cyber event, it could be a technical glitch, or it could be something else, right? And can we also measure the systemic risk? So because what happens into the economy that changes the way the payments has been transferred, and that could influence the systemic risk. For example, like if certain bank collapse, how it's going to affect the whole other banks or the other parts of the economy. So can we also measure that in a real time using this advanced analytics such as machine learning? And the third aspect is the payments ecosystem is growing faster and faster with the digitalization. So can we make use of this kind of advanced analytics to make to evolve with that design and make this new payment system more efficient? So in that aspect, again, we have a couple of papers. I will try to go with one of the use cases if I have time, but if I don't, then probably I have to skip one of the last one. But let's see. Do not skip the last one. Okay, the middle one. So let's do that. And just remind me like 15-20 minutes before. So this is the outline. I'm sure you guys must be familiar with the machine learning, what it is. So I will quickly go over that. I'm not going to go into the technical details, but I will be happy to take your questions or have one-on-one discussions if you want to go to understand the deeper aspect of that. And since we are going to look into the payments or the payments data, so I will give an overview of the data we have and we'll be working with throughout this presentation, and then how we can make use of. So these are the 3 use cases I have on the slides. So let's see, we can focus on first and second, and we can quickly glance to the second one. So one is how the payments data can be used with the supervised machine learning to make the economic prediction better. The second is how we can use the payments data and unsupervised machine learning to make them more safer. And the third is with the payments data and quantum computing together, how we can make them more efficient. So let's go to the machine learning. I guess, as I said, like most of you are familiar with, but I'll quickly go through that. So it's an application of AI, which can help us to automatically learn from the data. So the machine learning is not the AI, although currently people use them as a synonymous, but AI has something more to the machine learning. But again, there is the deep learning, which sometimes people think is a machine learning, but machine learning has something more than deep learning. And now if you focus the large language model, people think that is only the machine learning because that spans the most part of the circle, but there is more to that. And it helps us to develop the algorithm and computer programs. So how to make use of the data and learn automatically from the data by developing new algorithms and then writing the program. So that is the whole and soul of the machine learning. And it has been categorized into 3 aspects. Certain people say semi-supervised learning or reinforcement learning, also considered as a semi-supervised. But traditionally, this has been categorized into 3: supervised, unsupervised, and reinforcement learning. So I'll quickly go through those 3 examples and see how that can be used in the payments the cases I will be showing on. So the supervised learning is a very simplest part where we are trying to train the algorithm based on the examples. So let's say you want to train an algorithm to identify whether it's a cat or dog. So you take a lot of examples of the images or the actual data, and then train the algorithm that if this is the feature, then this is the dog. If these are the feature, this is the cat. So we have to have a target. So that's the output, and you have to have a predictor, so that's a set of features. And then here's an example of the neural network where these are the features and the Y is a target, and then you train the algorithm to identify as efficiently as possible. So it's either regression if the target is continuous, or it is a classification if the target is discrete. So there are various algorithms that can be used, starting with a simple linear regression, but now we can use like a tree-based algorithm. You can use a neural network. You can use the other advanced deep learning. And the second is the unsupervised learning. So here we don't have the target as such. So we use the input as the target. This is the one way to do unsupervised learning. There are various other ways. You can use the clustering of the data. So here we don't explicitly define the target. But essentially what we are trying to do is, like, if you have a certain features, let's say you are trying to again have an image of the dog, you want to reproduce that image of the dog as accurately as possible. But instead of using this N feature, you want to encode that information just in 3 features. So can we define what is dog or what is cat just by using 3 features or 2 features or 1? So something like that. So you're trying to encode information. So what is the use of that? Let's say if you have a cat image, then probably it would be very hard to reproduce that because you have only 3 features to extract all the information from. So you can use that to detect the anomalies. If it is not dog, then it is something else. So here we use only the features, and there are again certain classical machine learning approaches such as clustering, and then you can use the deep learning approaches like autoencoder. That is the one example I'm showing. And the third is a more I guess, traditional or the realistic approach, or the way human agents learn, is called reinforcement learning, is learning through the interaction. So here agents interact with the environment in order to create the model of the environment in their head. So you can define this agent as a neural network or some other algorithm, but essentially an algorithm is interacting with the environment, and as soon as you interact with the environment, you get to see the state. What if I interact with this? What changes? And what is the reward? So you can think of this as an example, like how babies start learning about the surroundings by playing, let's say, playing with the environment, play with the toy. They like the toy, that they get a positive reward. They want to play with more and more. Or in a video game, so you are started learning a new video game and you want to be more efficient. So you make some error and you get a negative reward. Then you realize that I should not be doing that. And that's how, but you have to do it like millions of times in order to generate this more accurate model of the economy in your head. And how we can use that into the context of the payments, I will just go through that in an example. So we saw this as a basic overview of the payments, machine learning, and what are the opportunities or how we can make use of that for to solve the various problems. I'm going to focus on the context of the payment system. So one of the things we can do, machine learning help us to do, is to solve the problem of the big data. So big data means it has high value, high volume, or it's a non-traditional, which is not traditionally not being used, such as language, images, or videos and audios, those kind of things. So we can process the big data. We can process the data which is coming with a very high frequency. Second thing is the non-linearity. If the data is, for example, during the COVID-19, everything break down, or there is a sudden change in the structure of the models. So that non-linearity probably hard to capture, but the machine learning are flexible and can help us to capture that kind of non-linear relationship between the data and the outcome. And they can help us to do the pattern recognition, those kind of unsupervised learning. And these kind of machine learning models they are very effective in doing that, and the automation. So there are various tasks, probably mundane but complicated, and you don't want to do that again and again. So you can train an algorithm to do it for you. So they can help us to do the automation. But of course, there is no free lunch. They comes with some challenges. And one of the key challenges, especially in the social science like economics and finance, is the interpretability. Because if you are making a decision, let's say as a central bank, you want to make a decision, and if you tell that the people that you cannot explain, just algorithm told me to do that, and I did that. That is not acceptable. So we have to be worried about that. We want to use something which is more interpretable. So most of the model, the machine learning has a black box in nature. That means you cannot go inside the model and exactly understand how it is coming up with that particular decision. And there is no causal relation. That is another thing which is key for the social science. You want to understand which factor is influencing how much, like that causal relationship. And that could be, again, hard to get with the machine learning. Although being said that the literature is evolving to incorporate the interpretability aspect into the model. So there are some interpretable neural networks out there, but it's still early stage, I would say. Second thing is expensive to train. So they are really good to capture this nonlinearity, but it takes a huge amount of data and a lot of computational power to train this algorithm. And in many cases, you might not have that big computational power. That's why you can see that most of the big tech like a Google, Apple, those kind of coming up with this big model because they have these computational resources and the access to the data. So that aspect is there. So it might not be useful for everybody. In that sense, you might have to use the trained model given by those big organizations. Then high error susceptibility. So given the flexibility of this model, they are very easy to overfit the model. So you have a training data and you can perfectly replicate that data in sample, but then you try to use that out of sample and then your predictions are very wrong. So having that flexibility makes it more difficult to select the model. So model selection or the parameter tuning or the parameter selection is another key challenge we need to overcome. And the algorithmic fairness. So if your data has a bias, that bias is going to be transferred or is going to be into the algorithm. So your algorithm or the model is as good as your data. And if your data is biased, then that bias is going to be transferred. And we have to be care about that, because if you want to use that for, again, in the social science aspect, like for example, you are screening candidates based on for the interview, and you let the algorithm do that, and all the examples you have in the history are mostly males and fewer females, then your algorithm is going to learn that bias and going to select more males and less females in the first screening, and that will have this social bias into the decisions the algorithm is making. So of course, we are talking in the context of economics or finance. The econometrics is one of the traditional way people have been doing all these kind of things. Of course, there are very sophisticated econometric models out there which can model the large scale data, which can model the nonlinearity, but where the machine learning can help. So I would say there is a hypothetical line. This is not, this is just a qualitative, not a quantitative, but there is a hypothetical line along the data complexity, which could be a large, the size, the scale, the type of feature, the number of features, or the, so big data, you can say. As we go along this line, the data is big data. As we go along this, along the left, we are dealing with the small data. And the model or the accuracy gained or the advantage of using machine learning. So here, we don't need to use probably machine learning, but as we pass this hypothetical line, probably we will be better off using machine learning in terms of, again, to get, if your objective is to gain the accuracy. And I have a simple analytical note on that. So where I try to look into literature, especially in the economics, and when they use this kind of model and what kind of model they use and how they use. So if you're interested in that, I have the link there. So let's quickly go through the payments data. Again, since I'm going to use the data coming from these two systems, I will quickly overview that. So in Canada, we have two systems. One is the retail and one is the wholesale payment system. So the retail payment system you can think of as your debit card or credit card. So let's say you went to a store and you use your credit card, and now that payment, your bank issued that credit card or debit card. That payment has to be transferred to the merchant who owns the account in the bank B. So now bank A, on behalf of you, have that obligation to settle on the bank B. So this is the smaller cycle, and we can get to see some of the data flowing through that cycle. And then there is a high-value payment system. They don't settle the payments on the transaction by basis, like at this small scale. They settle these big obligations created by all these kind of payments at the high bank-to-bank system. So there is no merchant here, but like let's say hundreds of customers went to a certain retail stores, and hundreds of merchants accepted those payments. Now bank A has a total obligation because some of the merchants, some of the customer might have account with the bank B, and some of the merchants might have account with the bank A. So there is a net balance between these two. That balance will be settled in the high-value payment system. And there are certain other types of payments which can flow into that. So we'll get to see the data from the retail, and then we get to see the data from the wholesale payment system. So in Canada, we have the CDSA or the automated clearing settlement system is the retail payment system, which settles small value payments. So it's still small. Like in 2019, we settled about 33 million payments daily, on average about 30 billions. But in the high value payment system, we settle about 200 billion payments, but only about 40 to 50,000. And the types of payments is like when you make take out the money from the ATM, the checks is still there. If you want to pay your mortgage or your payroll is being deposited into your account directly. So those all kind of payments, certain business to business payments, certain government payments. And here we have your stock exchange, CDX settlement from certain government payments for the other central banks, international payments. Those are settled into the high value payment system. Okay, so that's a quick overview. Again, it was, I know that it's very quick and might not be too familiar with the data, but the general aspect, what that brings us to in terms of the new things to play with. And the most important thing is the timely, because payments data is available immediately at the end of the period. So for example, as I just showed in the motivating example, that we can see even at the minute level, that how the data can be used to gauge the state of the economy. So that the timely aspect is the main thing. And the precision, because most of the economic data is a survey based, that means it's not 100% accurate, but this is not a survey, it is the actual settlement data. So it's a more precise, so there is no measurement or sampling error in the data. Then the high frequency that we can see the data at the transaction level or the daily level, because in economics is mostly monthly or quarterly. That's where we see the data, but here we can do transaction level or daily level. So that is a high frequency in nature. And in Canada, we have about 15 plus years of good data to work with. But again, there are some challenges. We might not be able to use this data for everything. because there is some missing information. Not all type of transaction is being captured through this system. So there are certain type of transaction goes to some other system which are not managed by Bank of Canada or the Payments Canada, who owns and operates the payment system in Canada. So we have some missing data. And many of the data is traditionally being collected for the regulatory purposes. So they don't collect all the information that could be very useful. So they collect only limited information. So we have a missing features. There are many changes happens. Like we used to have a checks as a prominent payment method. Then the debit card was introduced. So debit card being started to use, then the credit card, now the instant payments, QR code or mobile payments. So many technological changes. Nothing changed in economy as such, but because of this technological advancement, we just moved from one payment method to the other payment method. That creates this shift, and we have to deal with that. And the privacy, because this is a personal data, so protected data, we might not be able to use all the data or all the information which comes with the data. So we have to apply some privacy preserving technique and so on and so forth. Okay, so let's look into the use cases. So I'll use take the first use case. So how do we make use of these machine learning models and the payments data to monitor the economy and do the predictions? So what is the motivation here? I think because most of the key macroeconomic indicators such as GDP, inflation, and unemployment, this comes with a lot of delay, and they have a lot of uncertainty because they are sample based and they are being revised regularly. Sometimes a couple of years after their original release, they revise again. So that can tell us that there is a lot of uncertainty. And there is a lot of nonlinear thing happen, especially during the crisis. For example, this is the global financial crisis in 2008. And then we have this COVID-19, early COVID-19 period, where we can see that sudden changes in the GDP. So here I'm showing the blue line is the GDP and how it is going along with a couple of payment stream. I will not go into the details, but these are the couple of payment stream. And at least just you plot them on top of each other, you can see that they go hand in hand during the crisis. And sometimes they don't go opposite compared to other variables. So that can help us that essentially the timeliness and error-free and the broad nature of the data, that we have a variety of payment stream being captured, although not everything, but most of the stream we have. And the machine learning model can help us to deal with this kind of non-linearities or the sudden changes with the data, and how to manage if you have multiple streams or multiple data or multiple features. So I will not, yeah.
What is encoded paper?
So encoded paper is like automated. So anything that is based on the paper, like check is the encoded paper, demand draft is the encoded paper.
And digital transactions.
AFT is automated fund transfer. So like you have pre-authorized, let's say your credit card, your electricity bill is being directly deducted from your account. You pre-authorized it. And AFT credit means like deposited into your account. AFT debit means taken out of your account. So we have a simple model. So we have a base case. So we try to predict the GDP of the current month using most of the data which is available. As you can see that we have to use 2 months before GDP to predict the current month GDP. So imagine you are in the COVID-19 period and you have to use January or February GDP. It doesn't have any information about that. So your model is not going to predict well, because neither CPI, neither unemployment, none of them had information about the COVID-19. And then we have a couple of indicators. I will not go into the detail, but they are at a time T. So they have certain information. So because we want to see the time aspect of the payments, and then in our main case, we add the payments, which is again at time T, which has the information about what is happening in the current situation. And then we compare these two cases. So we tried linear regression, but then also we tried the dynamic factor model, which is one of the traditional econometric model, which is being used and that can capture certain types of nonlinearity. And then we use the machine learning. So we tried a variety of machine learning approaches, but in our case, gradient boosting regression worked well. And I will show the results for that. So these are the results. So we try to, let's say, predict January GDP on the 1st of February. That's what we are trying to do. 2 months before the actual GDP will be released, which is in the 1st of April, but we can tell the estimate of that on the 1st of February. So this is what the error we get, RMSCs. Then we add the payments data with the dynamic factor model, which is a traditional econometry, how much we reduce, and then we add the machine learning. So overall, we get about 15 to 20% gain just by adding payments data with a traditional econometric model. And then we see that the machine learning can add more accuracy gains especially during the COVID-19 period. So I'm not going into that particular time aspect of it, but the most of the gain we are getting here are during that COVID-19 period, which is out of sample. Yeah. So the whole objective is here, like, forget about the machine learning, just by using payments data and the econometrics, can we gain something? Yeah.
Something bothers me. The payment data is real time. GDP and the rest are past.
Past, yeah.
Yes. And payments in time t depend on GDP in t minus 1 and t minus. Is that not true?
So you are saying payments also depends on the previous.
But can you like run a model just with the payment data?
Just with the payments data. Okay, yeah, we can do that. But there's
a possibility.
Yeah.
Of hard correlation.
So one of the things we do is like also data-driven approach. So even T minus 2 GDP is there, we let model see if it want to pick or not, or whether you want to pick some of the payment stream only. But in our case, the data-driven approach, every time they pick the GDP at T minus 2, because during the normal time, there is a lot of information in that variable. So it did value a lot during the normal time, but during the crisis time.
That's the point. I think the point is that in the payments data, the information of GDP, past values of GDP also featured there. So it's
I see.
Featuring 2 times. So I think one way you could potentially address it is keep it as a second order model. In the first order, first replace payment on all of the other expected payments. Take out the residual.
I see.
So on the payment residual rather than all of payment.
I see.
Then in your model, then plug in that residual, which
Okay.
is orthogonal now to the rest, and then run that one.
Okay. Now that's a very interesting view. I don't think people have tried that, because every central bank has a paper where they use the payments data. But they just, because that's been traditionally, this is how the people have been doing. So the most simplest benchmark people use is T plus 1 by using T minus 2, because that's the latest available. And then they start adding, can we add inflation? Does it help? Can we add unemployment? Does it help? Can we add payments? Does it help? That's how people have been doing, but I think this is very interesting idea.
That's the problem, because that's the reason one cannot do inference on that.
I see.
That's why you can do forecasting, but you cannot do
Inference. Exactly.
So if you optimize it, I think you will get a solution to this in a more statistically correct manner.
Okay.
I mean,
No, I think that's a very interesting. Yeah. So our motivation is prediction.
It's a question of dumping more features and trying to see if reliably you can
Exactly.
get a lower delta or RSM.
Yeah. But that would be a very interesting thing to look at, that as well. Yeah.
Just the curiosity on the data on payment, that would be an aggregation of all the credit payments as well as debit payments.
So it's like we have multiple stream like
Credit card payments that happen time period T,
T.
and that is added to check payments that happen in that period.
Not added. So we use as a separate. So we see in a system, like, because these check payments are settled in a different stream, then the debit card payments are settled in a we don't have the whole credit card data here.
When you showed the tracking
Mhm.
data, payments was one line, right?
I just selected 2 of the stream. So we have about 40.
Payment would be multiple features.
So we have about 40 in terms of 20 value and 20 volume. I just showed a couple.
From a prediction standpoint, it doesn't really matter.
Yeah.
But interpretation would be, well, you have to worry about the credit card payment may lead to a debit payment later to settle it. Therefore, there is a
Yeah.
problem.
Yeah.
But if you are doing just forecasting,
Prediction, yeah. No, I think that's our objective, but again, now started people looking into that. Can we do interpretation? And this aspect was very interesting. Yeah.
Just one question. What's the interpretation of those values?
Interpretation?
497.
Oh, it's a RMSC. Yeah, root mean square errors. Yeah.
How do you deal with multiple values?
So No, that's a good question. So this gradient boosting regression or random forest regression, they inherently can deal with the multicollinearity, so we don't have to worry about that. But when we're using dynamic factor model, we have to worry about that, or linear OLS, we have to worry about that. So we don't explicitly model that into our economy. We chose the model which has shown in the literature can deal with the multicollinearity.
My last question.
Yeah.
So the second one is a random forest. Am I correct?
Yeah, gradient boosting regression. Yeah.
You know, in what percentage of the cases the sheep's payments data? Payments data is one column or multiple?
It's a multiple 40. We have 40
40
columns.
different.
Yeah.
Do you know in what percentage of the trees?
So what percentage, in a sense, like we do this feature importance, and I have that plot. Maybe I'll show it at the end. That where it shows that when the payments data is highly valued, when payments data, some of the payment streams are highly valued and some of them are not. Okay, so let me just quickly go through the example. So this is just during the transition of the COVID-19, February, March, and April. So at the start of the February, where we did not have any influence of the COVID-19, we can see most of the payment stream has a positive signal and trying to push the GDP in the positive direction. So this is the actual GDP, and this is what the model is predicting. And during the March, where there was some influence, as you can see, the signal coming from the payment stream almost all of them are still on the left side and has a positive signal, but the quantity is small. So this arrow shows that how much it is influencing in terms of the future ranking. But as you can go into the April, where we had the most influence of the COVID-19, all the streams had a negative signal and trying to push the GDP downward. So this is again not an interpretation; it's just a feature importance. Which feature is influencing how much in that for that particular model, and this is a month-by-month basis. Okay, so let me quickly go through maybe the third case directly. I will skip this through that and. So I will just quickly show you that what we are trying to. So we are trying to build a framework to extract this fraudulent activity, whether it could be a cyber or something. And we are trying to do it in 2 levels because the data is big and there are not many examples in the past to train the data. So that's why we have to use the supervised learning, unsupervised learning. But still we are trying to have this in 1 layer where we do this payments classification. And then the second layer, we do this anomaly detection. So essentially you can put this as like an airport security, where in the first level, they have a machine where you go through that. If it makes a sound, then this agent is going to check you. Otherwise, it will let you go. So same thing. So we have this payments classifier, which is based on certain known target. We train the model. If the payment is correctly classified, we don't bother with that. But if payment is misclassified, we collect all those payments and train another model, which can help us to identify how critical those payments are. So that's what essentially we are trying to do. So we use this something called supervised learning classifier, and then in the second case we use called isolation forest. But let me directly go through that. So this is the real transaction, and these are the artificial transactions. So when we train the model, on average, the anomaly score, which just tells us that how anomalous it is or how critical it is, it goes up almost double. And in every transaction, whenever you make it anomalous or change certain feature, the anomaly score goes up. So that's how we try to interpret like how well our model is doing. But if you have a question on that, we can come back to this. Okay, so the last case I want to discuss is the quantum computing and how to make use of that for the payments, improving the payment system efficiency. So we have our working paper, and if you want to go get into the details of that. So the motivation here is very simple. It's an NP-hard optimization problem, and I will tell you why. So given, let's say, batch of payments submitted to the system, we want to find the settlement order with the lowest liquidity usage. So every time bank make a payment, they have to have an assets equivalent value of the payments deposited at the central bank. So that means, let's say you are making $10,000 of payment, you have to have $10,000 worth of the asset at the central bank. But if I make you a payment, you can use my payment to send me back the payment. You don't need to put your assets. So then you might wait so that I will receive the payment and I will just use that. But I can think of that and I can also wait. But then the whole system will grind down to the zero, or it's called gridlock. So they have an incentive. They don't want to delay, but some of the customer might get angry. They have this critical deadline, but you couldn't settle their payments, and then now settlement didn't happen. So they have to worry about that delay and liquidity usage. So that's the thing they want to care about. So we want to find the order which can help us them reduce this liquidity needed without adding any delay. So we fix the delay constant because we collect a batch of payment and try to find the order in which they should be settled so that the liquidity required is less. I will have an example in the next slide. But essentially, if you want to do that, let's say you have 3 payments, it's a 3 factorial. You can settle them in a 6 possible ways, those 3 payments. But if you have 100 payments, it's a 10 raised to 158, which is a number bigger than the number of particles we have in the universe. So essentially, it will take a long time if you want to find all the possible combination. But of course, you can do optimization, and that's what we are trying to do. And that's where the quantum computing we think can help us because it's a combinatorial optimization problem. So it's a fundamentally new type of computing, and it's a stochastic in nature, as opposed to if you see the classical computing, which is based on the bits, which are clearly defined 0 and 1, but the qubits can be in a superposition of the.
I didn't quite understand the problem here. So every time one plane is kind of given, the problem of settling it right then and there, what is the cost of that?
That would be high. You need a lot of liquidity. So let me give you an example. Let's say 2 banks, A and B, having to pay each other $1 twice. So the original order is A, B, B. So let's say I'm A and you are B. I sent you $1, I sent you $1. And then you send me back $1, send me back $1. So in order to settle those first 2 payments, I need to put $2 liquidity at the central bank. Okay. So that's the liquidity is needed to settle those payments. You didn't have to put because you just revert back my payments. But if I do this in this way, I sent you $1, you send me back. And then I use that $1, send me back. We need only $1 liquidity. So find the optimal order in which we need the less liquidity without further delaying the payments, right? We still settle them payment immediately as they came in the queue, but in a different order than they came. That's the whole objective. I should have put that as the first. Anyway, but I'm not a quantum computing expert. I have learned through the project. We collaborated with the people who have more expertise. But essentially what it tries to do is perform computation by utilizing different properties such as the superposition. For example, the qubits can be in different states as a superposition of the 0 and 1 or the binary states. It can do the entanglement and tunneling, which can help us to accelerate the convergence or the optimization problems. So this is what our problem setup is. So given the batch of payments submitted to the system, we want to find the lowest, the order, which is the lowest liquidity used. And we want to essentially have an algorithm which can help us to do that. So you have these end payments. So we have put them in the quantum optimizer. This is the original order when we get this a new order, and then we will settle them into the payment system. And that is the example I gave you, that instead of doing this ABB, which takes a $2 liquidity, you can settle them in ABAB, so that we saved almost 50% of the liquidity in this case. So I'm not going into the details of that, just a couple of minutes I have left, but this is, we had to do the lot of benchmarking to prove that quantum computing can help. So this is the original, like we tried this simple algorithm they use in the payment system. So essentially, if you have a very large payment, which can need a lot of liquidity, you just settle that payment at the last, right? So it's a bypass the biggest payment. Then all you can sort them, put all the small value payment first and the large value payments later, so that you can settle all the small value payment, which takes less liquidity, and then use that liquidity to recycle these large value payments. Then this is a CP, is one of the well-known classical combinatorial optimization solver. So it still uses the classical computing, but it can able to solve the problem. And we also have a payment system simulator. So these are the actual payment system being in place for every country. So we use the one which have in Canada, and then we use the CQM. That is the it's a form of a solver which you can use with a D-Wave. D-Wave's quantum computer. So that is the quantum computing. As you can see that the total liquidity, average liquidity we can save by end of day is proportionally higher in the using quantum computing compared to the actual system with some restrictions. And then the classical solver, of course, classical solver, you get a lot of savings, but in some cases, it takes longer time for classical solver to solve. So you, in some those cases, it's not practical. Let's say it takes 1 hour to get this kind of saving using the classical, but you have only a few seconds because next batch is ready. You cannot delay this batch further. So with that time constraint, we would able to get higher savings using the quantum, proportionally higher. So these are about like a 250 millions in total, but the gap is, you can see, it's not too big, but the time aspect and the consistency is the key. And if we increase the batch size, our savings increase proportionally with the quantum as compared to the classical. So that is the key thing we think here. For this particular batch size, the gains marginally small, but with the higher, it is scalable to the higher batch, and then we can have a higher savings. So how many payments you have? So the example I gave here is the batch size is 4, right? We have 4 payments. So you can do this one in your head. You don't need quantum computer, but 4 factorial. So you can still do with a pen and paper. But let's say imagine with the 70 payments. It's a 70 factorial. And we went up to 700 payments, but the current quantum computer takes a longer time and it's not practical. So we forced our algorithm to do it for the 70 batch and 140 batch. And we see how much we are getting the scaling compared to the classical and the quantum. Okay, so that's, sorry, go ahead.
So you settle 7 payments that the first 7 you settle them, then you go to the next set. And the objective, the maximization, is probably that the turnout. The objective is how much money I don't have to
put. Yeah, how much money I save. Yeah.
And then when you go from 70 to 120, does that make any difference?
Yeah, the total savings, the total liquidity we need is still higher for 140, but the savings is high.
That makes sense, but proportion. So you are saving on 120 cases, so obviously then the size is going to be large. But proportionally, is there any value to it?
Yeah. We might have to wait a little bit longer. So there is a cost, because collecting 70 payments might come in, let's say, in our case, it comes in 90 seconds. On average, in 90 seconds, you have next batch ready. So we have about 90 seconds to process the payments on average. But when you go from 70 to 140, we have to wait for 3 to 4 minutes. So we have a higher delay cost, but the total savings we are getting from this higher batch, because we have now bigger space to explore, more payments to recycle, right? And that can, algorithm can utilize that to save more liquidity.
That's slightly possibly dumb question, but what I was thinking is that these kind of problems, I mean, even that they're in here, basically what happens is that it exponentially explodes.
Yeah.
So going from 70 to 71, you are literally multiplying it by 71. Then if you go to 140. Yeah. So therefore, going from 70 to 71 is not really 2 times. It's way more
than that, exponential.
So if we, I mean, obviously the start space of the integrator. So in that case, it may make more sense, I'm just thinking, to solve it in smaller batches. So if you solve, let's say you have 140. If you do it at one go, you have to search for 140 factorial number of combinations. Whereas if you do it in 2 batches, then it becomes 2 times 70 factorial rather than 1.
No, I understand. So, from computational point of view, you are 100% correct. But let's say this example. If I try to optimize instead of 4 payments, just first 2 payments, do I have any potential to save any liquidity? No matter I send my first payment first or second payment first. So having more give us this more recycling opportunity.
No, that part I agree. That, I mean, I understand that going by my argument, then one can just push it to on 1 or 2. But I'm just wondering if there is a kind of soft switch somewhere in between where you have the kind of ability to solve for, let's say, 100.
I see.
But you do not go to 200 because then it becomes like exponentially.
I see.
That was sort of my question.
Okay.
It's going from 70 to 140. Is it more?
So we do have that kind of plot where we go proportionally and then see how much savings we are getting and how much delay cost, and then we select that 70. So we did not randomly select 70. Maybe I wasn't clear that we did not randomly select 70. So we started with a 10, 20. We did not go 70 to 71, of course, like 10, 20, 30, then 70, then 80, 100, 140. We went up to 700 to see what is the weighting cost and how much proportionally gain we are getting.
Some kind of a loss function combining these two.
I see.
does it look something? I'm just
Yeah, no, that's a good.
looks something like inverted U that between 0, 10 to 700 there is kind of a soft spot, sweet spot somewhere where if you go beyond that. So there are two things. One is the liquidity cost, the other one is the computational cost. So if you define a loss function as the, let's say, squared sum of both.
I see.
Is there a interior optimal somewhere? And
It's there. We didn't go that way. We just plot them and chose it. Another thing we need to consider there is the number of feasible solutions. So it's a stochastic, right? It's not giving you every time the same solution. So we have to do this like 1,000 simulation. And how much feasible solution? Feasible means it's real. I mean, sometimes it gives the solution which it's not practical or doesn't satisfy all the constraints. So that is the key thing. So we have three aspects. One is the time, like number of payments, then the computational time, and the number of feasible solution. So with the current quantum computer, when we went from, let's say, higher and higher, like a 700, we couldn't get too many feasible solutions. There were only 1 and 2 feasible solutions. That means it's not solving it efficiently. But as we were staying close to like around 100, we were getting higher number of feasible solutions. So you have more confidence. Again, it's a stochastic. In a deterministic setting, you know that whether you are reaching or not. Here is a stochastic. So more feasible solution you are getting, more confidence you have that your algorithm is reaching something potential. So we looked at that, but I guess you are saying that you can embed that as a loss function into the algorithm itself and optimize for that while doing it. Something like that, right? Yeah.
I have another question before that. Is there, this is not my domain. When you say that you put a batch of 70 versus 140, when you do batches of 70, you take the first 70 transactions and you try to optimize.
Yeah.
Get them cleared first.
Yeah.
Before you go to the
Second batch, yeah.
But while you are clearing the first 70, the second 70 will show up and wait.
Yeah. So we have to clear it before the second batch is accumulated. Yeah, exactly. Yeah.
So the next batch doesn't have to wait.
Yeah. So that's our constraint. So when you use a classical computing, in some batches, it has to wait longer time so that third, fourth, fifth, sixth batch is already waiting. In many cases, it could able to solve.
Savings that you get from a larger batch has to be traded off versus the
Waiting time.
larger batch means that it could be a possibility that they're waiting for the fellows are on the bench while you are trying to solve.
Yeah. So we have that. Sorry, I didn't put those slides, those charts. So essentially, the waiting time goes linearly up. The batch size goes up. The time it takes to collect that batch size linearly goes up. Average time.
The batch size also increases the benefit.
Benefits, yeah. So we have to trade off between this liquidity or benefits we are getting through liquidity and the delay cost we are getting by waiting for longer time.
So that gives you a perfect solution as to what to do the batch size.
So again, this delay cost is more like it's based on the bank, right? Let's say if you are a big bank, you don't want to delay any payments. You don't want to disappoint any of your clients. You care more about, settling. So you value less to the delay cost and more to the liquidity cost. If you are smaller, it could be opposite, right? You are smaller bank, you are liquidity constrained. So you are okay delaying the payments, but you don't want to use too much liquidity. Yeah. There is heterogeneity in the payments.
It's not following the
No. So this is, as I said, it's a proof of concept. Yeah. So this is a proof of concept. The whole idea is to see, can quantum computing help, and does it good enough at this point so that we start exploring it?
The other thing is, and again, I know this optimization. You showed me a monotonic increase in the payment from P4 to whatever P4 to something else. That remains consistent, right? Because there's a logical reason for the benefits. The monotonic is.
So
many times in machine learning, you say that, well, what benefits you get from an algorithm also depend upon the sample size. Is there a possibility that the same exists there?
So
depending upon the kind of data that you dump in, the monotonicity may not work that way.
I see. No, it could be possible. So no, we are extending. Yeah.
Is there a possibility to theoretically prove
I see.
that CP,
CQM, yeah.
will necessarily give you a non-negative sort of a benefit compared to the other. So delta K can never be negative.
I see. We haven't explored that. Yeah. Yeah, probably. And we expect that people would pick up on this and do all these things.
Sometimes it's a shot in the dark. It depends upon the data, which methodology gives you a better benefit.
Yeah, so we have to try multiple methodology, but yeah, so that's the hope. Like, if you are into the theoretical aspect, you can take our algorithm and build a theory around that and see if it converges.
Something that is not guaranteed.
What is not there? That bar chart. Can you please show that bar?
So this quantum computation works better than classical computation in certain classes of optimization problems.
Which means that, yeah, but I'm more concerned about the fact that here we are trying to find out benefits based on a certain kind of data. If tomorrow that sequence changes, will this benefit also change? It means that it doesn't really, you can't come up with a solution which is.
But these are not results for one day. We took a random sample from 3 years, so that the order is very different for each of this day. Yeah, it's still an empirical result. So now we are trying to extend this to the different system, which has more banks, more heterogeneity. Yeah.
It's a very formative idea. Right?
Mhm.
If you are for each of these payments that there could be some interrelation within this set of data, right? So think of it from a network perspective. You can find out that nodal payment, and then because ultimately sequential ordering problem.
Yeah. Yeah.
You can't then just target the nodal payment directly rather than.
So that has been the traditional approach to solve this problem. So people have used the network and like a bilinear coordination, multilateral coordination, bilateral coordination. So that's how the people. So the current system we have, it embodies those kind of things.
So how would that be integrated with
Quantum, yeah. So separate. I see. No, I think those are good extensions, I would say. Yeah. No, you can combine those, come together, and that could be a good extension as well. Yeah.
Yeah, but I can also see that that's a different problem. So basically, then you're saying that let us somehow squeeze the space by saying that if certain people makes, some claim A, people will claim A, it's very likely that he is going to also make a claim B. So therefore, we can expect what is going to be the sort of sequence. So it squeezes the subspace. But here, I think the objective is slightly different. Here, the objective is more like in an agnostic manner, given a sequence, what is it's more like it's kind of optimization efficiency thing. Regarding that, I have a question before turning it over to the audience. Have you tried any case where you know what is the global optimum? And then see how quickly quantum computation reaches the global optimum vis-a-vis classical optimization? In other words, when you are generating this U sequence out of P, what is the guarantee or what is the assurance that you have that it's actually pretty close to the global optimum, not getting stuck in a local value? Yeah, so we started with a very small problem, like 5 payments, where we can solve by pen and paper, by classical, and then quantum. Are we reaching the same solution? Because we know that there is a fixed solution. Then we try 7, 10. We could go up to 10 because then it is becoming too many, because we have to do brute force to get the global minimum, right? So we did that at the start to make sure that our algorithm is doing what we want it to do. And then, but after that, we couldn't able to verify whether it's a global. For this case, like a 70 payments, we don't know whether it's a global. But if we let classical computer run for longer time, it is reaching essentially similar or very close to what we have with the quantum. And sometimes slightly better, sometimes very small with a small margin. So we have all those statistical results in the paper, like how many times it exceeds, how many times they are reaching the same, if we let the classical computer run for as much as the time takes to solve that batch. I'm very curious about that because there was one paper I was doing on a very high dimensional vector representation, hundreds of variables. So the maximum likelihood surface became 10,000 dimensional. So then at that time I did not even know about this quantum computation or whatever. And in any case, it's a smooth function. So we employed something like genetic algorithms.
I see.
It gave us some answer.
I see.
After the paper was published, then I started scratching my head and thinking that what if that is a local solution rather than a global solution, because we do not know whether that is really maximized or not, especially in this hyperdimensional setting. So I'm always curious about that. Any other questions? Yeah.
There are ways you can set up number. Let's say between 2 and 1, let's say set a buffer of 1.5. So that 0.5 the bank will always commit. So if there are small payments, that will go through the buffer itself.
I see.
And in the
I
next
see.
cycle,
I see.
that buffer will replenish.
So you are talking about the payments value. Okay.
Small payment,
Yeah. Yeah.
we have a small batch size.
Yeah. Now that's a good idea. So those are like practical. When we want to take this to the real system, I think they have to go with that, because there is no point in trying to optimize if it is $1,000 payments. We care about this large value payments. So yeah, that's a good point. Thank you. Yes.
70 payments and 1.5 minutes like that. How many banks were there? What was the number of payments?
So in our case, we have about 17 banks. So in our Canadian system, they allow only large financial institutions. I guess in India, if you want to do that in RTGS system, they have about like 400, 500 banks. So that number of players matter. So now we are extending this to the other like European system, which they have very similar to what we have here. So does it matter? How much does it matter, heterogeneity? Does it help or does it hinders the benefits? So that's the next objective. So we are going empirical way rather than the theoretical way they are suggesting. But I guess if somebody is good at theory, that would be a good application to look into. Yeah.
So we were talking about the multiple machine learning models, random forest and how we are coming up to the number of trees and like optimal parameter to over there.
Yeah.
Because there when we deal with a random forest and these type of ensemble models we're talking about, there is a high chance of overfitting.
Yeah.
Then how we are dealing with it?
So you do the cross validation to select the best model out of sample. And we came up with a very interesting cross validation approach. So traditionally you do this expanding window approach where you select the sample. So we don't touch this part. This is out of sample. Then we select this into the batches and train the model, predict it, and on average see which model performs the best out of sample on this set, right? So
either we do random parameter selections and we do cross validation.
Yeah, exactly.
But cross validation selection takes a lot of time and takes more of cost.
It does.
What is the case? In random selection, there is a high chance we lose the best optimal parameters also.
Yeah, there is always that possibility. So you have to expand your discretization a bit more.
So sometimes you
Competition.
for the costing also.
Yeah. So you have to give a budget. That's what they do when you do auto ML, right? Automated machine learning. You don't define anything. You define time budget or you define computational budget. This is the budget I have. Can you give me the best model? So there has to be some constraint. Yeah.
Yeah. So are there any questions in the chat?
No, man.
Oh,
Okay.
All right, so just ask me the last.
Yeah. Basically.
How much computational capacity do you have? How long does it take to solve this 70 batch?
Oh, for the D waves, the quantum computer, it was less than 5 seconds on average. Yeah.
What about 140?
140, I think 15 or slightly more. So it was not linear, 15 seconds or more. Yeah, on average. Yeah. So that otherwise is not practical. Then we can use the SIP classical solver if we don't have that.
I
So
was thinking about defining a different objective function. We'll talk about it.
yeah, sure.
One note I have is using this payments data. Here we have solved the liquidity. Can you use this payments data or have you used this payments data to solve on consumer and there are creating better, analyzing the patterns, creating better services, offers. So it's that is
I see.
the regulations are going to be because it's personal.
Yeah. So at the central bank, our objective is not that because we care about the payment system as a whole. We don't care about individual bank as much. I mean, I'm not saying we don't care about, but our main focus is on the efficiency of the system as a whole. But people are doing that, but they are private banks. They don't disclose everything.
What kind of regulation should they take?
So I guess it's both are evolving parallelly. So regulators are trying to understand how they are using it. Do we need to regulate how much it? So AI is still, in practical sense, is at least in fintechs or banks, is still evolving. And we want to we are trying to learn how they are using, which services they are optimizing, automating, and how that might influence the systemic risk and as such. So it's a step-by-step process, I would say.
As far as where else can you see this payment data other than
Where else is the payments data? So now we are trying to take this payments data outside the payment system itself, because as you can see that one thing we did is like trying to predict the GDP, which is like trying to do, but then they are trying to do something else. Like for example, like Silicon Valley Bank, they collapsed. So did we had any signal coming from the payment system which tells about that, okay, this particular bank is not doing very well or is not healthy from economic some sense? Can we get this signal earlier? So people are trying to do that, but one of the things with the payments data is protected, and only certain people have access to that. It's not, this generated data is not being made public. So otherwise it would have been more, there would have been more innovation, but unfortunately they cannot do that because there's a lot of personal information.
Right, so it has been a fascinating talk and lots of good discussion. So let's thank you.
Thank you.
Here is a small memento for you from
Thank you.
our center.
Thank you.
So thank you.
Very kind.